Okay, now it's recording. So thank you again, Susana, for giving the seminar today. So the word is yours. Yeah.
Thank you, Professor, for inviting me. Okay, thank you all for being here. So today I'll give the lecture in English, okay, about uncertainty and risk analysis. But feel free to ask me questions in Portuguese, or if you don't understand a specific part, you can write me here in the chat and I can repeat in Portuguese, so no problem, okay? So basically, I'm Susana. I'm a researcher at Petroleum. I did my PhD with Professor Dennis, okay, his supervision a couple of years ago, and I did my thesis really on this area, so on uncertainty and risk analysis. So that's why I'm going to share with you some of the main topics related to this. Okay. So so basically, this is the outline of today's presentation. Okay, I'm going to divide it into three main topics. Okay, the first one is about uncertainty characterization. So I'm not going to talk specifically on how we characterize uncertainty, but where does uncertainty come from, and how we can represent them statistically. Just very, very brief, this first part, okay? Then we're going to talk about the production forecast under uncertainty. So you have seen about reservoir simulation, how we can use it to forecast production. You have seen how we can deterministically optimize a production strategy. But now you'll see about the probabilities, probabilistic forecasts. Okay, this is a typo I have here. Okay, so you're going to see about probabilistic forecasts, meaning that we are going to incorporate uncertainties in the process, and we are not going to have just one forecast, but a set of possible forecasts of our reservoir. Okay, we're going to talk about how we can generate what we call scenarios. Okay, I'm going to define scenarios as well. We're going to talk a little bit about production economic indicators. So this is not really the topic of today. I believe you've seen that about in previous lectures, but I'm just going to go very fast about it. And I'm talking about these because the indicators we choose are important for our uncertainty analysis and our risk analysis. So we're going to have what we call a risk curve analysis. We're going to see also what is a risk curve, okay? And then we're going to understand how can we analyze and quantify the risk curve, okay? Then I'm going to talk briefly about production strategy selection under uncertainty. So I'm going to assume that you already know what the production strategy is, okay? But if you need, I can answer again your questions. I can remember you and give just a little bit summary of what the production strategy is, the kind of variables you're talking about. So please feel free to interrupt me anytime you want, okay? Either in the chat, but I will monitor the chat here, so I think I will be able to see everything. But if I don't see the chat, I'm sure that Danielle will help me, or Professor Dennis, or if that doesn't happen, you can interrupt me with using your microphone, okay? So no problem about that. Okay, so then the last part, so we are going to talk about how can we manage uncertainty. So from the first two parts of the lecture, we're going to see where uncertainty comes from, okay? Then on the second part, we're going to see how we can study and quantify and understand the effects of uncertainty. And on the last part, we're going to see how can we use that to make better decisions, okay? This is going to be the big three parts of today's class, okay? And in this last part, we're going to talk a little bit about what we call representative models. Maybe you have seen that also in the previous lectures. And we're going to talk about the three key actions we have to manage uncertainty, okay? We have information, flexibility, and robustness, okay? And you will see that sometimes I use words that are a bit different from those that you see maybe in other papers. We always use about manage uncertainty, not mitigate uncertainty. And we're going to see why I don't say mitigate uncertainty, but to manage uncertainty, okay? This sometimes the words we use are important, okay? So let me skip slides. Good, so the first part, okay? So first, some of you, I'm not sure about your background, but sometimes we are used to hear about uncertainty in exploration phase, okay? So, and I brought you this figure here to say that the life cycle of a petroleum field or a petroleum reservoir it's very large, okay? And depending on the phase we are in, we have to see the problem differently, okay? So when we talk about the beginning, where the key players are the geologists and the geophysicists, so the geoscientists, they see the problem in a very different way that we do. So they have different kinds of uncertainties that they are mainly focused on. So the methods they use, the techniques they use, the goals they use, and all that will depend a lot on the stage we're in, okay? We are, so basically in the beginning, okay, when we still have a very few information, if you read papers about risk analysis and so on, you will see that the main uncertainties are related to the petroleum system, okay? Those of you that did the class on petroleum geology, I'm not sure if the course is that with Professor Battiselli, he will talk about that, okay? What is a source rock, what is a reservoir, what is a trap, migration, and so on. So they are concerned here in understanding if there even is a reservoir, if there is oil in that reservoir, okay? And for us, that we are a little bit forward in the chain, we are more related. We already know that we have a reservoir. We already have concrete data on the reservoir, but we really need to understand better how the fluid flows inside the porous media. We want to understand specifically and study in depth the properties of the rock and the fluids. We want to study how much oil we can recover, okay? And that's where the production strategy comes in, okay? Because when you are in the beginning of the field lifetime, you have so little information that you have to use much more simple methods. Okay, so in here, we are much more concerned about all of these topics that I've put in this box. So, and this is where we are focusing in this class, okay? Also, this is a second figure that I wanted to share with you, really about this, on how the timeline, so you have here the timeline, okay, you have exploration, appraisal, development, and production. You have here the range of uncertainty. So in here, you have the maximum level of uncertainty, and you have here the minimum or certainty, okay? And in here you have estimated ultimate recovery, so how much I have recovered. And here, okay, you see that you have the maximum uncertainty in the beginning before you started the exploration, and as time goes by, you will understand better, and when you abandon your field, maybe I'm going to put the pointer here. When you abandon the field, it's when you are absolutely sure of how much you have produced. You will never be sure of how much you have left there, okay? So we are only certain of how much we have produced. So this is an example of how uncertainty can vary. This is actually just an illustrative figure, and we can have actually, this does not need to be linear. At some point, we can understand that the reservoir, for example, is much more complex than we thought before. So we can have an enlargement of the range of uncertainty. So this is just an example. But the idea I wanted to give you is that the amount of uncertainty will vary, okay, as time goes by. And only in the end, I will be absolutely sure of how much I have produced, okay? So basically, when you are talking about exploration, if you read papers and so on about exploration, you will see that uncertainty in volumes in place is their biggest problem, okay? And they use very simplified reservoir modeling techniques, okay? And also the kind of decisions they're evaluating are much more simple than the ones we are evaluating. They are talking about more what we call go or no go, which is, for example, declare the commerciality of the reservoir and go forward with the development of the field or abandonment. So this is much more simple as decisions here. Actually, much simply means the amount of variables. Okay, they are assessing, not in the kind of it's easier or less important. Okay. When we are talking about the appraisal, development, and management phase, okay, which is where we are today, we are talking about, as I said, uncertainty in fluid flow characteristics, about recoverable volumes, production over time. Okay, so we need much more complex methods, okay, than the ones used in exploration, so that we can understand how our production strategy affects, okay, the behavior of the reservoir on the complex integration between the production strategy and our reservoir. Okay, so and this is not why you need the complex method. So you can select the production strategy under uncertainty. Okay, this is what we're going to see soon. Okay, well, what is this uncertainty? And we need to remember that we're talking about very high investments. So we're talking about drilling wells, investing in the production unit, and so on. So we have here the decisions are very complex because we have many variables. They are very dependent on each other, and they're also very dependent on how certain my knowledge is, of how well I know my reservoir. Okay, so we need to use more refined reservoir modeling techniques and much more advanced reservoir modeling techniques, and this is where reservoir simulation comes in. Okay, so we need the use of kind of reservoir simulation. We don't really need, but it's highly recommended. Okay, there are other ways to obtain production forecasts, but reservoir simulation has the unique advantage of capturing the effects of the production strategy on the performance of a given reservoir scenario. Okay, and this is I believe you have seen in the previous classes, but again, feel free to ask me if you need. Okay, so then, but we also need to deal with the computational costs of all of this. So we are talking about very demanding methods in optimization, as you have seen. In simulation itself, we have, for example, in the pre-salt cases, we have very complex reservoirs. So we need to use very advanced reservoir modeling techniques. So we can capture very well all the heterogeneities of the reservoir or all the phenomena that happens inside the porous medium. Okay. So basically, where does these uncertainties come from? Sorry. So basically, we have on the one side, which is obvious, okay, it's the reservoir uncertainties, okay, as you all may have seen before, okay, I think from one of the first lectures on reservoir characterization, we are dealing with our physical system is not accessible very well. It's not accessible at all, okay, so all the data we have are either acquired sparsely, okay, the direct data we have, which is like the drilling, each sparsely, okay, it's very distant from each other, but mostly it's obtained indirectly, which is from seismic data, well logging, all of that is indirect data, okay. The direct data is the core samples, is the fluid samples, okay. So we have to understand that we have a very big physical system, okay, the reservoir is enormous, and we have very limited access to it. So all the properties that you have seen in other classes of reservoir engineering, for example, all those rock and fluid properties, okay, that we need to characterize very well in our simulation models can be uncertain. I'm not saying that all of them will be uncertain, but all of them may be uncertain. So we have to understand all of those rock and fluid properties, so rock properties, fluid properties, rock fluid properties, and so on. So, and we need to, all of these will lead to uncertainty in our fluid flow prediction. So what I put in my simulation model, okay, will affect the forecasts, okay. When we talk about forecasts, I'm not sure if that word is also familiar to you. We are talking about how much oil and all the other fluids over time we produce. So we're talking about the production curves and injection curves over time. So we talk about forecasts. Okay. This is so all the way I understand and the way I characterize my reservoir. Okay, the type of porosity I say it has, the kind of PVT data, it will affect, right, the production curves. Okay, that's an obvious relation. Okay, so that's why we need to understand and be very careful, okay, in what we inform in the reservoir simulator. We need to be very careful, and when we're not sure, it's better to put it a larger uncertainty range than to go for like with the feeling, and then if you are wrong, it can have very important impacts. And this comes in another dimension of the problem that I will not be talking today, which is the decision biases, okay? Because everything we do, okay, or most things we do are led by a human, the engineer. So everything we do, we need to understand that many things, sometimes it's not the problems in the method, the problem's not in the data, the problem is how we use it, okay? So, and then we have talking about decision biases. So everything we do, you have to be very careful not to be biased in the way you analyze and you characterize your problem. Okay, so then we have here the fact that this is actually the last point I put here is not so much uncertainty, it can be more seen as an error, okay? So we need to understand that our reservoir, the way we represent our reservoir into the numerical simulation models, it's a simplification in itself, okay? We will not be able to, our physical phenomena happens in the porous, okay, at the scale of a porous, but our simulation grids it in the scale of hundreds of meters. So in itself, it's a simplification because it's the way we can, in a timely manner, simulate our problem. So in that, we are also introducing some errors in the problem, okay? And that will also affect our forecasts, okay? Not only my understanding of the reservoir, but how I put it in the simulation model will also affect, okay, the grid I choose. So, and that will come from the lecture from Manuel. The grid I choose, how I model the fluid model, all that will affect my forecast. And in here, we are talking about limitations of our techniques, okay? So, but we are not only concerned about the reservoir. We have other sides of the problem, okay, which I have put in this slide, okay, that we also need to understand. So on the one hand, you are all familiar with the time scale of a project, okay, from the petroleum industry. We are talking about long-term projects, so about 20, 30 years, many times much more than that, okay, depending if it's onshore, if it's like the oldest fields, they can have many more years, okay? So how the economy will be in 10 years or 20 years, that's a big question mark, okay? So we need to understand that there are other factors, okay, that are from the outside of the reservoir part, okay? This has nothing to do with the reservoir, okay? But so if I could have like the most perfect information and I could have access to my reservoir and know it exactly well how it is, I cannot escape from this side of the problem. These are other types of uncertainties that are also present, okay? So we have the idea that because we are exposed to all the markets, okay, so we have uncertainties on how it's going to be the oil price, the gas price, the geopolitical uncertainties, we can talking about wars, so that's all a big question mark, and this needs to come inside our simulation problem, okay? We need to take all of these into account, so all the economic and geopolitical uncertainties, because they will affect market variables, okay? Market variables will be oil price, gas price, and so on, capital expenditures, so all the investments in the production units and so on, all the operating expenditures, okay, this is the cost of maintaining production, okay, so when we have a well producing oil, it has costs, okay, so all those costs that will happen during the lifetime of the field, so they are no longer investments, they are costs, we call them operating expenditures. This can also be a question mark in the future. They can be, and when we talk about the question mark, it's not only for the bad, okay, it can be for the good, okay? So we need to talk about also that, okay? For example, the oil price now is not so good, maybe in the future it can be better, okay? So we need to understand if the decision I make today, giving the current oil price, maybe I can know, I can have, it's not economically valuable to invest in something, but if the oil price increases in a couple of years, it can be, okay? So this is also an important factor that we need to weigh in our problems, okay? We have operational uncertainties, okay? This is very important as well, and we have been trying to understand how we can incorporate this, okay? When we talk about operational uncertainties, that again, because we're talking about long-term projects, the systems, the wells, the platform, and so on, they'll probably need maintenance, sometimes they're going to have problems and they have to close the operation. So this also needs to be weighed in our problem. We need to quantify the effects of that in the long term, okay? Because we are talking about the long term, we don't need to know exactly when the maintenance is going to be. We need to have an average of how is the performance of a well. Is like in 30s is like 80% of the time, is 90% of the time. How is the performance of that system? So we need to understand this because it will affect the NPV, right? The net present value, which I believe you have also seen before in the class of production strategy. And the class we're talking about technological uncertainties. Okay, this is also something a bit more difficult to incorporate in the process, and we're not going to talk on them today. Just an idea is that the technology I have today, okay, may not be enough to explore some resource, okay. But we need to understand that that's why the university exists. We're doing research so that we can develop new technologies, so that in a couple of years we may have new technologies and they can be feasible to address, like for example, the ultra deep offshore water. Before in the past, it was not possible. Then we had new technologies, so new fields or new resources became reserves, okay, meaning that we had the tools and the economic feasibility to invest in them. So this is also for the positive, okay. That's why we also need to understand that in the beginning when I talked about managing uncertainty and not mitigating uncertainty, because uncertainty can be good as well, and technological uncertainties is a good example that it can be positive for us, okay. We expect that in the future we will have better technology, okay. So here I have listed a couple of examples, okay, on reservoir uncertainties. So as we said, porosity, permeability, the structure model of my reservoir. So this will affect how we build the grids, okay, the simulation grid, the connectivity barriers, fluid saturation, fluid contacts, relative permeability curves, and so on, okay. Operational uncertainties would be, for example, the production system availability over time, as I said, the well productivity. Economic uncertainties, oil and gas price, fluid production and injection costs, and maintenance costs, okay. All of these are possible and examples of uncertainties, and we can have many more, okay. So, and how can we, okay, we know that they exist, okay, but how can we represent them in our problem, okay? And this is a very, very simple basic concept on statistics that I'll bring here today. It's not really our focus, but we need to understand how we can represent them, okay? So we use what we call uncertain attributes, okay, which it's different from decision variables, okay? So uncertain attributes, it's something that I don't know, okay, and I cannot control, okay, I cannot choose the value of the porosity. It's unknown, but I cannot choose it, okay. But well, when you talk about decision variables, it's something that I can choose. For example, the well placement, I may not know exactly what's the best well placement, but I can choose it, okay. So this is different. So decision variables don't have probabilities of occurrence, okay. We don't have a probability for well placement because it's subject to decisions, okay. When you talk about uncertain attributes, we have probabilities because we don't know, but based on the knowledge we have, okay, we say, okay, this is the most likely value, this is the range, and this is the probability, the shape of the probability curve, okay. And then we have basically the main three types, okay. We have continuous attributes, we have discrete, and we have just statistical realizations, okay. I'm sure that you've seen part of the things I'm talking about in the first lecture that Manuel gave you, okay. So when you talk about continuous uncertainties, okay, this means that they can take values between a minimum and a maximum, okay, within a continuous range, okay. For example, fluid contact, the contact of the water contact depth, that's a continuous interval, okay. Rock compressibility, fault transmissibility, oil price, all that is a continuous uncertainty because it can take a value between a minimum and a maximum and all those possible values inside the interval, okay? And they are characterized by a probability density function, okay, or a PDF, okay? Can be normal, like in this example, can be log normal, which would be like, it has like a shape like this. It can be triangular, uniform would be this example here. It means that every value inside my range is equally probable to occur, okay? And where does this come from? From the reservoir characterization part. So the team that study the data, that build the model, they will give us, like the team that is working on production optimization, risk analysis, the set of possible uncertainties, and they say, okay, this is, I cannot understand more how is the depth of the water contact. I cannot be, given the data I have today, I cannot say with more certainty the depth of the water contact. I have a range, and it's inside that range, and the probability is either like this or like this. So the team that studied the data, so the geoscientists and the geoengineers, they will give us all that mapping of the uncertainties that they know, okay? We can have other uncertainties that we don't know, and that's a completely different problem. But now let's talk about the uncertainties we do know, okay? When you talk about the discrete uncertainties, okay, now they can take a finite number of discrete values in no longer a continuous range. For example, the relative probability curves, okay? Usually we don't treat them as continuous between two possible curves. We treat them as 3, 4, 5 possible real perm curves, okay? So we treat them as discrete uncertainties, okay? PVT tables, the same way, we treat them as discrete. We treat them, okay, can be either this PVT table, that one or the other one, okay? The structural model, okay? Where is the grid top, where is the bottom, all that, maps, okay? All that we treat them as discrete uncertainties. I can treat a continuous uncertainty in the discrete way, okay? For example, to simplify my problem, if I'm talking about the water contact, I can take, for example, 3 or 4 or 5 possible levels, and it's much more simple to work with than a continuous range, okay? And the last one is the geostatistical realizations, okay? This came also from Manuel's class, okay? He talked about probably how all the modeling techniques that we have, so we use these techniques to characterize the spatial distribution of the petrophysical properties. So talking about phases, porosity, permeability, net to gross. Okay, so all that we use their statistical realizations. So they are treated differently from the other attributes because they are generated using a very specific method, which is a geostatistical modeling. Okay, and so we have a set, okay, of equiprobable realizations. So this is something that is important from the statistical modeling. We also always have a set of equiprobable, meaning that they have the same probability. So when we have geostatistical realizations, we cannot say exactly that this realization is more likely to occur than the other. Okay, they are all equally probable. Okay, so they are much more difficult to treat because we have hundreds of them. So we need to understand, okay, I have hundreds of possibilities of the maps, of porosity, of permeability, and so on, and how can we work with them? Okay, so many times they are very difficult to handle, unlike the other uncertainties. Okay.
Susana?
Yeah.
There is a question. Yeah.
Okay. Okay. What is range? Okay. Yeah. Exactly. So this comes from the reservoir engineering team, from the Manuel's lecture. So the geoscientists and the geoengineers. Okay. Given the data they have. Okay. They define. Okay. Given that the data they have, the precision of the tools, and all that, they will understand, and they have to define the minimum and maximum. And this is again where the decision biases come in. Okay, so can be subjective. Okay, because understanding your tools, understanding your data, really depends on the experience of the geoengineer or the geoscientist. Okay, but these come from that part. Okay, they need to understand, given the data they have, the amount of data, the precision of the data, the precision of the tools, and understand how can they be sure. Okay, this can be like an interval. Okay, it's an interval of possible value that they cannot define with more certainty than that. Okay, I'm not sure if I answered properly your question, but the general idea is that. Okay, good. Okay, thank you. Okay, was this first part clear? Okay, I'm not sure if everyone got it. If someone else wants to add something in Portuguese, it's okay. Okay, I'm going to take the silence as okay, as I can continue. Okay, so basically we saw where uncertainties come from and what type of uncertainties we have. Okay, so now we're going to talk about the production forecast under uncertainty. Okay, so basically we have came from the production strategy class. Okay, we have a production strategy that we need to choose. This is our challenge. Okay, in the reservoir engineering team, specifically today and last class lecture. Okay, so we need to define, this is our challenge. How can I produce oil or gas from this reservoir? Okay, and defining the production strategy means defining a set of decision variables, as I said. So we have to choose the platform, what type of platform it is, the dimension of it. When I'm talking about the dimension, I'm talking about the processing capacities of oil, water, gas, and so on. And we have to talk about that, how many platforms we'll have, where they will be located. Okay, we need to talk about the wells, how many wells, the types of wells. When I talk about type, it's not only its producers and injectors, but also if they're going to be vertical, if they're going to be horizontal, if they're going to be deviated, if they are going to have conventional completion or intelligent completion. So all of these systems in itself, they are very complex. Okay, and we have all of these, all the operating conditions, mean that I have decided to drill these wells in this place. Now, how am I going to operate this in time? Okay, so all of this is very complex. Okay, and this is what you have seen in the production strategy selection class. And we need to understand that all of these variables affect each other. Okay, so because the reservoir is a very complex system that it's many times connected or not, depending if you have flux boundaries. Okay, if you change the position of one well, it will probably affect the performance of other wells. Okay, probably they're no reservoir will have one way to develop it. You can have many ways to develop a given reservoir, and this is where I'm not sure how much in depth you went into optimization, but it's what we call local maxima. Okay, your optimizer can find one good solution, but it can miss others. Okay, that can be equally good or even better. Okay, so all the problem is very complex. Okay, and as we have seen, the production strategy selection depends strongly on the reservoir. Okay, and this again comes in our question. So if my knowledge is uncertain, if I'm not sure about my reservoir, how can I select my production strategy given that? Okay, so, and also the production strategy selection depends on the production facilities. Okay, meaning that depends a lot on the logistics as well. If you are offshore, what kind of infrastructure you will have there. If you have a high gas-driven problem where you have the gas production is a very problem for you, but you have no pipelines or no LNG, no way to export the gas, what you're going to do. Okay, so it depends also on that. Okay, and also on the configuration you have choose. Okay, And uncertainties again also affect the forecasts. Okay, so we have many things. Okay, you have the reservoir itself, you have the production strategy you have selected, okay, the configuration, and again, this again is dependent not only on the reservoir but also on logistics and restrictions you may have on site. You have uncertainties, okay, and you have again something that is risky decisions. Okay, it's going to talk about again this a little bit later. Okay, just I put here as a reminder, but I'm going to talk later. Okay, and how can we get these forecasts? Okay, the focus of this class is model-based reservoir simulation. Okay, so you use a simulation model to get our production forecast, but there are many other approaches. So many of you must have heard about the data-driven, which are based on machine learning and so on. But this is still today, it's progressing extremely fast. Okay, this kind of knowledge. We have other more ancient ways to get some more basic equations that you have probably learned in reservoir engineering class on how you can understand how much you will produce and so on. But for us, we focus a lot on production optimization using and production strategy selection using reservoir simulation because it's the best tool we have today to capture all these problems and all, not problem, but all these dimensions of the problem, okay? The reservoir side, the production side, the uncertainties, and all the integration between this and that, okay? So basically, it has some advantages. Just recapping, because I'm sure you have seen about this in Avances class. Okay, so it's physics-based. Okay, it captures the physical equations of the problem. Okay, this is again unlike any data-driven methods that are only based on data. They disregard the physical laws governing fluid flow in porous media. Okay. In this problem, they capture the physics of the problem, okay? This is where you can have the most accurate production forecasts in terms of because it integrates all the rock and fluid property from the reservoir, but also the recovery mechanism you choose, if it's water injection, if it's water and alternating gas, which is WAG, if it's polymer flooding, it can capture all that. Okay, you can inform in your simulator not only the placement of the wells, but how you will operate those wells over time, what you will be injecting, the rates, the pressures, and so on. Okay, you can use all of these in your simulator. Okay, consider production strategy, as we have said, and like some other equations that you can use or data-driven tools you can use to forecast your production. These the user, like the engineer, can go to the tool and select exactly the production strategy it's using. Okay, you can assess multiple variables. Here, variables, we talk more about objective functions. Okay, I should revise here. So you have many indicators. It's what I want to tell you. The simulator will give you a lot of data. Sometimes we have talked about this at UNIC, that sometimes you cannot process all the data the simulator gives us. Okay, it's humanly not impossible, but extremely difficult to handle all the data because you have very detailed data per well, for your system, per region, over time. Okay, it can give you all the indicators in terms of the fluid behavior. It can give you saturation maps. So you have all these indicators that you can possibly imagine. Okay, the reservoir simulator can give you. Okay, and using this, making use of all this data is also a challenge for us today. Okay, it also is something very important for NPV. I'm sure you have seen, but I'll come again also in a couple of slides. Is that something that is very important to talk about this NPV, which is net present value. This is an economic indicator that takes into account the value of money over time. Okay, you know that the value of money today is not the same that it will be in 10 years. It's not the same as it was like 10 years ago. So, and these are the speed of how much you produce. Okay, the shape of the production curve is if you produce more soon or if you produce slowly, okay, it will affect the NPV, not only the final volume produced, okay? Because it takes into account over time, okay, how much you will produce at each time, because it will assume that you will sell the oil in those dates, and depending on the oil price and the time value of money in that date. So this is something unique that you can get from the reservoir simulator, is the speed of recovery, okay? The disadvantages, okay, it's obviously it's time consuming, computationally expensive, okay, especially when you talk about these new kind of reservoirs we have in pre-salt, that we need to use very complex simulation models so that they can capture all the heterogeneities, okay, and they can we have to use specific grids to capture all the influence of the fluids, okay, the interactions. I was missing the word fluid interaction. Okay, you also need to capture that. So basically, you need to use you need to weigh in now the costs and the precision you have and the time you have to make your decisions. Okay, so that's where you need many times to use simplifications. Okay, but the problem with simplification is that we need them. It's inevitable. And we need to remember our representation of the reservoir in a simulation model in itself is a simplification, okay? We know that our models are always wrong. They are not an exact description of my problem, but it's the best I can get with today's computational infrastructure and human resources we have, okay? So simplifications are required, but we need to choose them with caution, okay? And this is also a focus of research, because we need to make sure that when we are simplifying something in the problem, we need to make sure that it's not affecting our decisions and the accuracy of our forecasts. And if it is affecting the accuracy, for example, if I use a very simplified model, it's very fast, but I know that I'll lose a very high percentage of the precision, but for that specific task I need, it's okay, because it will not affect the decision I'll make in the end. So this is also something that we always need to take into account. We do all these studies to make good decisions, okay? So if the way I represent my problem will affect my decisions, so I have here a problem, right? Because the effects of decisions will not be the physical problem itself, but the way I'm representing them in my models, okay? So that is why simplifications need to be chosen very carefully, okay? So I've listed here a couple of examples, so the classes of simplifications we can use, but it's not really the focus of today's lecture, okay? We can do simplifications in how we treat my simulation models. This was the focus of one of your classes. We talk about high, medium, and lower fidelity models, okay? So we talk about fit-for-purpose models. It's the ones the industry usually use, okay? But depending on what I'm studying, okay, if I'm doing optimization, I need to run thousands of evaluations. Sometimes I need to use lower fidelity models. They are not so precise, but for the type of evaluation that I'm doing with my optimizer, they're okay. If I'm studying really some phenomenon related to, for example, either polymer flooding, to WAG injection, something that I really am focusing on the physical phenomena that is happening, maybe I need to go to a more high fidelity model where I have a better representation of my problem. This is going to be for more detailed analysis. Okay, this is also something we need to choose. I will talk about the concept of representative models, okay, shortly, which can I see them as a simplification of the problem, still in the physics space, okay, but I'll not talk about this now. I'll talk about in a couple of slides, okay. We have also simplified treatment of uncertainties. So again, before we talk about the range of uncertainties, and I can, instead of using, for example, in a continuous variable, I can simplify it using a couple of values, not only all the possible ranges to evaluate how my production strategy affects all those possible levels, okay? I can select just a key uncertainties, okay, which is, say, for example, instead of using all those uncertainties I can possibly have, choose the most critical ones, and I think I have a couple of slides about this too. We can talk about proxy models, okay, we are going outside of the physics, okay, now it's going to be only based on data. I'm not sure if you have seen this too, but talking about decline curves, polynomial regressions, neural networks. So we are going outside the physics of the problem. So we do not use anymore the physical, the equations that model the physical problem. We just use purely the data and try to forecast the future basically only on data, okay? We can also talk about efficient sampling. I'm going to talk a little bit this about in the future. So basically this slide, it summarizes many things that I will talk in the future, okay? That's why don't worry if you don't understand everything that is showing here, just really a slide for you to have to guide your studies, okay? And you can use automated procedures, so you can use the go to the computational part of the problem, okay? So use for those of you who will be using or have used simulation, so you can not only simulate your problem using one node of your or one processor of your machine, or you can break that simulation into different processors of your machine, and it will go much faster. Okay, so you can use some go to the computational part of the problem. You have some new initiatives on hardware acceleration using the GPU and so on. So you have other ways to make your problem faster. Okay, so basically, but the key message that you need to understand is that we have many ways, okay, to simplify my problem, either in the way I treat uncertainties, in the way I get my forecasts, but the idea that we need to choose them very carefully so they do not affect our decisions. Okay, we can accept some losses in precision, for example, in the NPV or recovery factor, but we cannot accept if they will affect my decision. Okay, if it will be the truth of the simplification that will make different decisions, then that we have a problem. Okay, so coming about the production forecasts. Okay, I don't see any more questions. I'm not sure if everything is okay, if I can continue. Okay, I will assume so. Okay, please interrupt me. Don't worry. Okay, it's really the idea is that we share knowledge. Okay, so feel free to talk to. Okay, no problem. So I think you saw in the production strategy selection class how we can optimize for one reservoir model, okay? And we talk about that in the deterministic approach. Deterministic means that we have only one scenario that we are concerned about. We don't care about all the other uncertainties, and it's usually we do this deterministic approach using the most likely scenario, meaning that the scenario that has the most probability of occurrence. So given that range of uncertainties, I'll probably get this is an example, the range of uncertainties, right? The PDFs. I'll get the most likely value of each attribute, and I say, okay, this is my base case, it's the most likely. Or I can go and I can get some forecasts and say, okay, this is my P50 model. I'm going to talk about that as well. I can use like a model that is in the mid-range of everything, okay? And I call this a base case, and I work with that. So at the end, so I have, this is my attributes and my uncertainties and the probabilities of them. I only use one of the values, okay, to model my reservoir, and then I'm not concerned about the others, okay? We call this a deterministic approach, and we have one production curve. So we have time, and NP can be any other indicator, and I have one forecast, one production curve. When we talk about uncertainties, the idea is that here we have what we call probabilistic approach. Instead of having one model, I'll have many models, okay? So many possibilities of my reservoir. And this is where we define scenario, okay? So one scenario is a possible combination of one value of each uncertain attribute, okay? And this is also, so a scenario is a possibility of my reservoir given the set of uncertainties I have. So in the end, when I get my forecasts, instead of having one curve, okay, of my indicators over time, I have n curve for n models. Okay, a question. How do you run sensitivity analysis to identify uncertainties with more? Okay, I'll talk about that. Okay, that's a very good question. Okay, because if, yeah, I'll pause your question if you don't mind, in a couple, and I'll go back to that in a couple of slides. It's a very good question. Okay, so because if you remember, I said that we can have many uncertainties. Okay, so if I'm combining all of them, I can have very big number of models. So, and the V is asking, how can I select the most important attributes so that I can like control the number of scenarios we generate. Okay, so we have N models and production forecasts. So basically, here I have again a simplification. Okay, I think this slide was misplaced. Okay, we have continuous uncertainties represented in discrete uncertain variables. Okay, so this is what we're talking about. We have a continuous, for example, a continuous one. Okay, we can discretize them into levels, and then I can either simplify that using only 3 values. This is a very common simplification, and David is asking about another kind of one, which is the selecting which attributes I will choose. Okay, not sure why the slide is here. I'm sorry about that. Okay, so basically the question is here. Okay, sensitivity analysis. This was what David was asking about. So when you go to sensitivity analysis, I want to understand the effects of each attribute on my forecast. Okay, so I have a bundle of uncertain attributes. Okay, and I want to isolate and to say, okay, these I have porosity, I have water contact, I have rock compressibility. Okay, I want to understand how much individually these attributes affect my production curves. Okay, and we have different ways to do it. Okay, one way is what we called the one error factor sensitivity analysis, meaning that I get my base case, okay, which is like the most likely value for all the other attributes, and I vary, okay, all the possible values, okay, of this one. Okay, so I take the base case, and if I have this attribute with 10 levels, I will go and I will replace all the 10 possible values of that attribute, and I will simulate that. This is one way to do it. Okay, and the idea is that when we do this, I will get something like this, a tornado plot. Okay, this will gives us the range, okay, of the impact on when compared to the base case, okay, the dispersion of what this attribute is. Okay, and I can identify which ones are the most critical ones. For example, I have here 6 attributes. Okay, this one clearly has a very big impact in the negative one. Okay, so when compared to the base case, this scenario is most likely pessimistic in the other levels. I have here another attribute that also have big impact, so it's very important I consider it. I have this one and also this one. So, and these ones, because they are less than 1%, I can say, okay, this, given the precision of my reservoir simulation, given all the uncertainties, I can neglect these ones. Okay, and one way to do it is with this one I've seen here, but because David has asked, I'll talk a little bit about that. Is this one is called the one factor at a time sensitivity analysis. Okay, so I take the base case where everything is fixed, and then I will go and analyze all the possible values of each attribute, okay, individually. But there are other techniques, and in here you can use experimental design and also response surface. It's been widely used, because when you use experimental design, you can it's the other way to do it. You can account for the interactions between attributes. For example, if you isolate one attribute, maybe you will miss some of the effects it has when it's integrated with the other ones. So we can do a different way instead of doing this classical way. I have not put it in the slides, but I can give you some more information if you want after the class. You can use experimental design to choose some key combinations, okay, of the possible attributes, so you understand not only the individual contribution of each attribute to the variability, but also if there is important interaction between more than one attributes. Okay. So when you go, now I've talked a little bit about sensitivity analysis, where we want to understand which attributes are most important. Okay, I've seen one, but now the question mark is, okay, how can I generate a scenario? Okay, we said that scenarios are possible, one possibility of my reservoir. They are a particular combination of all the uncertain attributes. Okay, so one value for this attribute, one value for this attribute, and one value for this attribute, and so on. Okay, the question is how can I combine these attributes to generate the scenarios? Okay, and in our case, in this case of this course, one scenario equals to one simulation model. Okay, but this is not necessarily true. Okay, so basically we have three main classes, okay, of the width. Okay, we can use the derivative tree. Okay, we can use the Monte Carlo sampling, and we can use Latin hypercube sampling. These are the most okay.
Susana, there is another question.
Is it safe to use CMOS AI for the? I have not used it yet. I cannot confirm. I would say probably yes. I've used another software from another company. It's from Basic Front Lab, which is called Cougar. And they have very much more advanced ways. I think it will be interesting to see what tools they have. But my answer would be probably yes, because this will probably take into account using experimental design or any other more advanced tool with machine learning or so on, to capture the interaction between attributes in sensitivity analysis, and that can be very important. And I would say yes, but I am not sure because I have not tested it yet. I've used another software to do it. Okay, if you have more questions and you want to open your microphone, please feel free to, okay? Okay, you're welcome. Thank you, Danielle, for telling me. Okay, good. So basically, we have the derivative tree, Monte Carlo, and Latin hypercube sampling. These are three ways, okay, to combine the attributes. The idea that, okay, I have all these attributes. How can I select and draw one value from here, one from here, from here, from here, and say, okay, this is scenario one, okay? And these are three possible ways, okay? So the derivative tree, it's very outdated, okay, in the way that it worked before, and it can work, for example, maybe in exploration, but in our problem that we have so many uncertainties, and we have just statistical uncertainties, we have hundreds of possible values. This way of doing it became very unfeasible. The way is that you use a tree, probably learned this in statistics, to combine all possible levels of all possible attributes. For example, we have here, three attributes, A, B, and C, okay? A is divided into two levels, A0 and A1, and you have then B, so combine A0 with B0, B1, and B3, and the same one for A1 with B0, B1, and B2, and then you go with C, and you have C0, C1, and T2, and so on. So each one of these branches is one scenario, so have 1, 2, 3, 4, 5, 6 times 3 scenarios generated in the end. Okay, so you have scenario 1 will be A0 plus B0 plus C0. Scenario number 2, A0, B0, and C1. Okay, and you see that how it's easily, this becomes exponentially huge. Okay, so is the base case always defined as the most likely scenario? This is a question from Davi. Usually it is, okay, or we can do it the other way around, okay? You can get your forecasts under uncertainty, okay, and you select one that is like average values for your outputs, for indicators, okay? You can either do that, as you said, and as I said in the class, this is the most likely value for all my attributes, so this is, in theory, the most likely reservoir model, because I have took the most likely value of all attributes, but I can get forecasts, not select the base case a priori, but you can do it afterwards, after you get the NP, NPV, WP, and so on, and say, okay, this is a value that is close to the average of all the indicators. I will take that as a P50, okay? You can also use the volume in place. Some people do that as well, okay? I'll get the volume in place for all my scenarios and see one that is close to P50. Okay, there are different ways, and I think it will depend on the company, on the approach they use. Okay, I hope I could answer your question. If not, please say so. Okay, you're welcome. So basically, this is the derivative tree I was just going to tell you, because it has history, but we don't use it anymore because it's likely unfeasible to have hundreds or thousands or millions of scenarios if you have very large sets of uncertainties. Monte Carlo, okay, this is the most common one, okay? So the idea of Monte Carlo is that it does pure random sampling. What means is that it goes to attribute 1, or A, it randomly selects one value or samples, okay, this is the word we use, sampling. And you go to attribute B, C, and D, and so on. So if you say, okay, generate me 10 scenarios. So it'll go, scenario number 1, go random value from A, random value from B, random value from C, and random value from D. This is scenario number 1. Now scenario number 2, again, random value from A, and so on. Okay, so basically what it means is that this is, in theory, it works, and it has been used for a long time, okay? In many industries, not just the petroleum industry, but the problem is that it requires that you select, okay, a very high sampling number, because it's pure random sampling. Okay? You cannot control, if you just do, for example, 10 samples, that the random value for the 10 will be from here to here, okay? So this is a kind of a limitation of this method. That's why many times it is combined with a response surface and so on, with a proxy model, okay? Yeah, this is what I have in this slide, okay? Because it just does random sampling. You cannot make sure that it will sample your distribution evenly, okay? Here, okay? When we mean sample the distribution evenly, that you mean that you are covering the entire range of values, okay? You want to capture all of these scenarios. The idea is that when you go from these to the scenarios, the idea is that your scenarios maintain the same or approximately the same distribution. And if you are doing random sampling, pure random, you cannot make sure that with few samples you will make sure that you'll cover this. So you need to use a very high number of samples. And one of the problems that we can miss is the low probability but high consequence events. We can talk about these, for example, these tails of the curve. This is very low probable, very unlikely, but if this happens, it has a very big impact, okay? It's a very good scenario, very optimistic, and so on. The same thing for this one. It is very unlikely that this value happens, but if it happens, we have a big problem if we didn't consider that in our decisions. We can lose a lot of money, can make a very bad decision, okay? So that's why Monte Carlo required to run thousands or tens of thousands of samples to ensure that all of that is totally covered. Because it's very difficult to simulate tens of thousands, okay, we use many times proxy models, okay? This is not, I'm not going to go into depth, but the idea is that you do some key samples, some key simulations, and you construct a mathematical equation, okay, analytical equation, and then you bypass the simulator when you go you do the thousands of samples in the response surface, okay, and it's like it's really a mathematical function, okay, just really in the sense of that you go outside to the physics of the problem. I think that probably you've seen a little bit about this in one of our previous classes, the Avanci one, I assume. Okay, when we go to Latin hypercube, this is the method we have been using a lot at UNIC, is that it has some desirable features, okay, from random sampling, but it also does what we have is stratified sampling. The idea is that when you go to the PDF, okay, instead of drawing random values, first the method divides your PDF into intervals, okay, and you want to make sure that at least one value is inside each one of these intervals, okay? So if you do, for example, I have here 1, 2, 3, 4, 5, 6, 7, 8 levels, right? If you do 8 samples, the method will make sure that one is here, one is here, and so on. Okay, so the idea that it does random sample, but inside the interval, but it makes sure that you have all your intervals covered. So you can get a good coverage of your PDFs with much less samples than we do with Monte Carlo. Okay, so this is very efficient method. So again, we can get efficiency, and we can by choosing your methods wisely. Okay, so I have changed nothing here. I have just choose a different method, and we'll be able to get much more well my scenarios. Okay, so this again some more theory about the method, but you can read that later in the slide that you will have. Okay, so basically what we have been working on, so at UNICE, this is the reference for if you want to read more. I can, all the reference that I have here, you can ask me and I can send you after the class, no problem. Okay, the idea is that you use this idea of discrete of Latin hypercube, and you combine these with just statistical realizations. Okay, and this is a method we have been seeing that it has been working very well. Okay, it was a new way to do it. I don't think any other people have been doing, other research groups, I mean, when I say other people, this way of treating the problem that you use Latin hypercube sampling to combine all those uncertainties that we see and we discretize and we characterize with either continuous or discrete variables, and you combine them with statistical relations, and you get your scenarios. Okay, this is a very efficient way to generate the scenarios. Okay, nothing changes from here. Okay, the idea is that I do these and then I combine them with the statistical realizations. Good. So this is an example that I got from the web. Okay, not a work from us. It's just really an illustration on how, for example, here we have 1,000 samples. Okay, and here we have also 1,000 samples. I'm not sure the input data, what it was, but the idea is that they were sampling normal distributions. Okay, well, I think they were sampling the normal distribution. Okay, they had the normal distribution. Okay, and here they said, okay, let's do 1,000 samples in this normal distribution curve. And this is how the histogram is the result. Okay, you see that you have very many imprecisions. Okay, when you go to Latin hypercube sampling with the same 1,000 samples in this distribution, you see that how perfect it is, because before starting the method, it divided, okay, the normal distribution into ranges, and then it sampled inside its range. So it has a more it's a smarter way to do it. Okay, that's why Monte Carlo requires so many samples, and it becomes unfeasible to run, I mean, thousands and thousands of models. Okay. Okay, this is an example I have here from a work we also did on that. This is from in black is the curve from Monte Carlo with 5,000 samples, and here is from the Latin hypercube method with different samples from 500 to 20, and you can see that even with for example 300 is the red one compared to the black one, it's so close. Okay, so you see how you are reducing the computational time using this method. Okay, this is just the idea I wanted to show you. These are risk curves. Okay, by the way, I forgot to tell you, I think we have a slide better in the front, but the idea is that this risk curve is also called in the literature complementary cumulative distribution function. I'm sure some of you have heard about the CDFs, okay, cumulative distribution function, and they're probably plotted like this, the other way around. Okay, and in our case, this curve is constructed using each dot here is one model. So if I have 500 models, I'll have 500 dots. Okay, if I have 5,000, I have 5,000 dots. Okay, and we use the probability of occurrence of each one plus the output, okay, the indicator, the value of NP and so on, to construct these cumulative distribution functions. And this is what we call risk curve. Okay. So, and okay, now again, the recap I was talking about, the performance indicators that I mentioned in the beginning, is that we can do this risk analysis for the indicators we want. Okay, so we can talk about production indicator, we can talk about cumulative production of oil, gas, and water, oil recovery factor, we can have injection indicators, cumulative are the most common, rates are not so common, or risk analysis, and you have also the economic indicator, net present value, return on investment, internal rate of return, and so on. Okay, that's just examples, but not our focus. Okay, and the idea is that the importance, again, also here, just a recap from previous classes, is that the importance of having the economic indicators is that sometimes, but this also has to do with the strategic side of the company. Okay, sometimes national oil companies are more focused on the resources itself. Okay, so the oil, they are not so concerned about the getting the best economic return. Okay, but they are more concerned about getting the most resources they can get. Okay, so but that's not valid for all companies. Okay, that's why we have at UNICE have been showing a lot the importance of incorporating the net present value or other economic indicators in the studies, because sometimes it's we're talking about the maximum oil production, but at what cost? Okay, if I go and I drill 1,000 wells, okay, I'll produce probably a lot, depending on maybe it's the reservoir will not respond so well if I did that. But if I just want to produce a lot, I go there with no restriction and I do everything I can to produce. But will it be profitable? Will I get the most of my investments out of it? That's why we have shown that the incorporation of economic indicators are so important. Okay, and also again, this is the second part of the importance, is that some decisions incur additional investments, okay, or costs, and that's why it's important to consider them. For example, when you talk about acquiring additional information, we will see that in the future. Okay, in the second part of the class after the break, if I'm so uncertain about my reservoir, I can go and decide to buy more data, drill one more appraisal well, acquire more seismic, but it costs money. So I should include the economic factor into account to see, okay, how will that new information change my decisions? Okay, will it just confirm what I already know? I just want to be more comfortable in my decision, but does it have value just to be more comfortable or not? So, but it's also a complex answer. There is no actually right answer, because you'll hear some comments usually from the academia that has some ideas about that. From the industry, probably you'll hear some other ideas. Okay, this is very complex question to answer. Okay, but it's important to always remember that everything we do in the petroleum field has a cost, and we need to weigh in when we make our decisions. Okay, this is the typical E&P cash flow. I'm not sure if you have seen it in previous classes. Okay, if you have, I will not go into depth, but the idea is that we have here all the pre-development costs. Okay, this go before the reservoir engineer comes in. So we talk about geological studies, seismic, and so on. So when we have here the acquisition of commerciality discovery, it's only here. Okay, so all of this is before the bidding rounds and so on, after the bidding rounds and before declaring the commerciality of the case. Then you have more investments on drilling more wells. This is where the reservoir engineer part enters with the appraisal. Well, you want to understand better your reservoir before you make your decision. Then you have the field development starts here. Okay, which it's marked in here with this box here and the red arrow. And you have then the capex, as we talked. Okay, so we have a lot of investments on drilling wells, buying production units, manifolds, and so on. And then we have, when you start production, okay, this is here, you start having revenue. So you start selling either oil, gas, or both. Okay, but you also start having new costs, which is the royalties, taxes, and so on, and also the operating costs, the costs of maintaining your platform. You have some fixed costs there, which is the personnel, cooking, and so on, and you have the variable costs, which will depend on production. Okay, and then at some point in time, you start having profit. Okay, when your revenues, okay, surpass all your expenses at some point. And you have here, and then you have at the end the abandonment. This is a typical E&P cash flow. It's always good to have it in mind, so you can understand that everything we do has a cost. Okay. So, and here the NPV equation that I leave you for your reference, okay? The idea is that the NPV is the sum of discounted future cash flow. So the important message here is that it's an indicator that it takes into account the time value of money. That's why it is so important. And it's very important to use it because when you choose a production strategy, sometimes you can have two strategies that in the end they have the same recovery factor or the same NP, but how fast they produce the oil, it will affect NPV, okay, as we said before. So this is a very important indicator for us. It's the most important indicator, actually. And the idea is that a positive NPV indicates that the project earnings generated by a project, okay, projected earnings exceeds the anticipated costs, okay? So if you have a positive NPV, usually it's a go-ahead, okay? We can proceed with the project, okay? And again, it's also very important to look at, when you look at the NPV, at the maximum NPV, okay? Because when they have the bidding round and so on, they have a contract, okay, for 20 years, 30 years. And what we do in reservoir engineering in our studies is also to look at the entire NPV, okay, not only at the final date of the maximum date for field abandonment, because sometimes the costs become so high and the revenue so low when, for example, in the most common reservoirs with the water injection, we start producing so little oil and so much water that it starts to having negative cash flow, okay? And at this time, what happens is that your NPV starts to decrease. So you need to understand what's the maximum NPV so that you can choose wisely on the best time to abandon your field, okay? So but NPV is calculated for one reservoir scenario. It's one value, okay? When we talk about uncertainties, we need to shape those indicators a little bit differently to understand, okay, how can we incorporate them into uncertainties. So before we talked about NPV, which we calculate for one reservoir model, when we talk about EMV, it's the expected monetary value, we calculate for an ensemble of models, for a group of models, okay? And this is the NPV, it's multiplied by the probability of occurrence of that scenario, okay? But we'll see this in a second, okay? And sometimes using this value, which is like an average or an expected value, we can use this for other indicators. You can have the expected recovery factor, the expected NP, and so on. But this is just an average value, okay? So you'll see that we have other statistical indicators, okay? This will be related to the risk curve that we'll see in a second, that try to capture how the shape of the risk curve is. So there are some statistical indicators that probably some of you have heard about, like standard deviation, coefficient of variation, which is the standard deviation divided by the expected value, percentiles, okay, I'll talk about them in a second, amplitude, and so on. These are some standard statistical indicators that have been used in the literature. So probably sometimes if you read some papers and some books, you'll come across these indicators, okay? But okay, I've spoiled here a part, okay? The choice of those indicators need to be made carefully, okay? So in here, I started this slide saying that uncertainty is different from risk, okay? I've already gave you the answer. And my question to you, I'm not sure if anyone wants to open the microphone and talk about that. Why do you think I say that uncertainty and risk are not the same thing, okay? Does anyone wants to try and answer that? Okay, no volunteers? Come on, guys. Okay, I'm sad that you're not interacting with us. Please don't fall asleep. Make sure that you're there, okay? So basically, uncertainty and risk are not the same thing, okay? And what we say is that uncertainty is what comes from the lack of knowledge, okay? If I'm not sure about something, I say that I am uncertain, okay? I'm not sure, I don't know, okay? But given the current knowledge and the current data we have, I can characterize these uncertainties with PDFs, ranges, and what we have seen before, okay? I can characterize them, but I'm not sure about them, and that's uncertain. Risk is something different, okay? Risk refers to the probability of unwanted outcomes. Risk is something that I do not want, okay? Uncertainty is more general, and risk can be inside a part of the uncertainty, okay? Is the part of the uncertainty that I don't want, meaning that it's like the failure to achieve a targeted return. So I want to get that, and if I'm not there, this is bad for my project. So this is undesirable, so this is risk, okay? So, and I'm saying that the risk is a part of uncertainty, or can be, depending on the range of uncertainty, because uncertainty can have that part of the risk, which would be like the pessimistic values of my reservoir, but it can also have what we call upsides, okay, meaning that it's the optimistic side of the curve. You have the base case, remember, you have pessimistic values, and you have optimistic values that are better than the base case. So those cases, I cannot call them risk. They're not risk, they're good. An optimistic scenario is not a risky scenario, okay? That's why we say that it's different, uncertainty and risk, okay? This is a very important definition, and if you're not clear about that, please say so in the chat, okay? So basically, this is the risk curve again, okay, as we have said, okay? So we have cumulative probability. So we take the n scenarios, we take the probability of each scenario and the NPV, and then what we do is that we calculate the cumulative probability and we plot the risk curve, okay? And so I said in the previous slides, 3 main definitions, okay? Uncertainty, okay? I talk about risk or downside risk, and I talked about upside potential, which is like the optimistic. Okay. Thank you, Jose, for the feedback. Okay, and so basically, how we want to show here is that, for example, for us, uncertainty is how variable my returns will be. Okay, I'm not sure about if my returns are going to be minus 1 billion or 3 billion. Okay. So I'm not sure about that, so that's uncertainty, okay? But if my results are here, this is not bad, this is good, okay? So I cannot say that all of this is risk. And in some of those statistical metrics, okay, that sometimes you will read in papers, at UNICE we don't agree so much with them because they see all the variability as risk, okay? And that's not completely wrong in some cases, okay? If you go to, for example, to the market or to the stock market, okay, where you can earn and you can lose money if a stock value increases or decreases depending on your position, okay? So variability means risk. Also means opportunity to gain, but also means risk, depending on how you plan your portfolio and your strategy, okay? So that's why when people imported some knowledge from economics and from the markets and so on to the reservoir engineering, some of the concepts were not so adapted like perfectly. We need to adapt them to our problem, okay? And that's why we say, okay, we don't agree that all the variability of my curve, all the spread is risk. We don't agree with that. We say that all of this is uncertainty. This is how uncertain I am about my NPV. But the risk is, again, what we saw, it's something that we don't want. So if it's don't want, it's in relation to what, okay? I don't want what? For example, in this example here, okay, I'm sorry, it's not so perfect round number. It's like, for example, 800 million. So if my project is, okay, for me, the desirable NPV for a project, if I'm a big company, is 800 million in this example. If I don't get that NPV, this is not good for my portfolio, and for me, this is risky, okay? If you are a very small company that for you just wants really to have profit, don't need to have very big project, for you the level of risk can be like 0, okay? Meaning not level of risk, the benchmark for your returns, okay? Because, okay, if I don't get, for me, the bet is to have negative NPV, which I'll lose money. But if it's positive NPV for me, if I'm a small company with small onshore projects, just those mature fields, for me, I'm not looking for big with billions of dollar projects, okay? So in those cases, so this is why we use this definition of risk, where you have the benchmark, and the benchmark is defined by the company, okay? So depending on where they are, or the profile of the company, the portfolio they have, and so on, they say what risk is for them, and it can also depend on the type of project you are, okay? So for us, risk is also only what is below what we want to achieve, okay? If we are up above that, okay, we say that we have the upside potential, okay? So this a term that I got, like in a paper from my PhD thesis, also from the economics literature, okay? So this is not actually something new, these concepts. They are new in the reservoir engineering, okay? So not a lot of people have used them, but I think they are increasing this idea of different interpretation of the risk curve. The idea is that, okay, if I'm on this side of the curve, I'm above what I really need to achieve, that's good for me. So let's see how can I exploit, how can I make value of those side of the curve, okay? And we have used these new indicators, again, new in reservoir engineering, but not so new in other sides of economics, okay? Where the standard deviation for us does not measure risk, it only measures uncertainty, okay? How my risk curve is spread, okay? We use lower semi-deviation, okay? Here, lower semi-deviation is only the deviation below our benchmark, okay? And the upper semi-deviation, the deviation above the benchmark. But the difference really here is that in our equation of the semi-deviation is not like half deviation. We don't use the expected value, unlike in the standard deviation. We use the benchmark, okay? This is really a new adaptation of the equation, okay? So basically, as we said, the benchmark is defined by the decision maker, okay? It only depends on his definition of loss and gain. And when we are comparing a set of production strategies, for example, here we have 9 risk curves, okay, I think. Each risk curve comes from one production strategy. So we have, to understand better this graph, so all the curves have the same number of dots. I think it's around 200 in this case. Each one is a model or one scenario, okay? And I took those 200 scenarios, okay? And I used 9 different production strategies. I was like, okay, and I went, okay, how each one of these production strategies perform in these 200 scenarios, okay? And I got the NPV for each one of them, and they are distributed here, okay? So each one of these curves represents the performance of one production strategy, so one placement of wells, one platform capacity, and so on, in the 200 scenarios, okay? And I see how this risk curve is much worse than this one. Worse because look, all the values are so low compared to this one. This strategy here can have 1 billion loss, okay? And at the maximum, it reaches like not even 2 billion, okay? This green here, the light green one, you see how this is a much better strategy for this set of 200 scenarios. I can get much more return, okay? And level of risk is close to 0, okay, here, okay? Level of risk, no, level of negative NPV, okay? Risk for us, it's defined as the benchmark here, okay? So when I marked here in this dashed line, it becomes much easier to read using a visual inspection of the slides, how different the risk of this curve is, okay? If my level of risk is marked here, see how risky these 3 decisions are, okay? All of the curve is below the level of risk, acceptable risk. Well, this set here, although the dispersion is much wider, okay, these curves are not so dispersed, they're much more short, but half of my curves are above my benchmark. So this is much better solutions, okay? And this is the example, okay, of how we can understand with these indicators. So these are cross plots, okay, of EMV, a standard deviation, lower semi-deviation, and upper semi-deviation, okay? And I wanted to compare these three examples, okay? This is just an idea for you to have. So if I look here, so if risk is here, I see, okay, risk for the blue and the green one are similar, right? And for the orange one is much higher, okay? If you have EMV versus risk, I see that in this plot, okay? The risk for this one is much higher, okay? I want to minimize the risk. For these ones, it's similar. And I can also compare the EMV, okay? So here, this solution has higher risk and a much lower EMV, while these ones are much better, okay? And we see, again, the positive side of the tail, we see something similar, okay? We see here how the tail here is so small, okay? The upside potential is very, very low, is here, okay? I want to maximize upside potential, and I want to maximize the EMV, okay? So the solution S9 becomes so similar, okay? So attractive here. And we see here, it's so clear how it is so much better than the others. If we use the standard deviation, which is a very common metric, the plot does not give us that interpretation. It seems that, okay, for us, S6, the orange one, is the least risky one, okay? Oh, I have a lower AMV, but it's so less risky, but it's not so true because all the points on my orange one are below. For example, if I talk about a cumulative probability of 50%, I have in the orange one 1,000 million NPV, and for the same probability, strategy 9 gives me 2 billion, okay? So that's why we visually say that, no, this risk curve is not so attractive. This one is much better, even though it is more variable. That's why it is so important to choose carefully our indicators, because depending on the indicators we choose, we can go to false analysis and to choose like suboptimal or even wrong decisions, okay? And this is an example of how, if we use a better interpretation of the risk curve with better indicators, we can get much better decisions, and we can automate our analysis, because if my indicators are right, okay, I don't need to go and visually inspect and confirm that my indicator got it right. I can easily automate many of the methods, okay? So because I have an indicator that quantifies precisely what I want, so I can do everything automatic, okay? So I think that for me, I'll do a break here. Danielle, Professor Dennis, I'm not sure if you agree. For me, I'm approximately halfway my slides.
Okay, Susana, I can stop the recording here.
Okay, thank you. So we'll be back in like